So graphene is actually a family of very diverse materials. So that you may not realize that. So a single layer of graphene is an interesting. It's a zero bandgap semiconductor, and you can make what's called a field effect transistor out of it. But graphene has a cousin, and that's two graphene layers stacked in a particular crystallographic arrangement. It's called bilayer graphene. And bilayer graphene is a very different species. It has some unique properties. It can, if you apply an electric field to bilayer graphene, you can actually distort its electronic structure. You can give it a band gap. And once you have a band gap, then you can you open yourself up to other kinds of applications, to sensors, but also digital electronics. And so we're very interested in producing graphene inks in my laboratory. We're interested in coatings and barrier materials. We want to use the barrier properties of graphene to control which types of molecules can get at an underlying surface. So my group last year produced the first graphene ink that was enriched in this bilayer type, and we also have a separate ink that's enriched in what was called trilayer graphene, which also has a unique set of properties. The reason why this is important is because graphene is going to play a very large role in making new kinds of coatings that essentially are for all intents and purposes massless. But imagine that you could coat a surface and change absolutely nothing about the properties of that surface. You can barely detect this coating, but you can completely shut down its ability to be corroded. So you can completely block molecules from transporting through the surface. Think of very small plastic films that prevent molecules from passing through them. One application is hydrogen. Hydrogen is a very hard molecule to contain. Even in a steel container, the hydrogen is leaking out. It's embrittling the steel. So if you could make graphene coatings that are barriers, you could potentially make new materials that have properties that humans have yet to see. Completely make materials that can seal and contain. And if you make a perfect barrier material out of graphene, you can also talk about designing porosity in the graphene to make new kinds of membranes for water purification, gas separation, and other processing technologies. So we're working on that in my laboratory as well. It could lead to new materials that are extraordinarily corrosion resistant, materials that you can. So when it comes to designing materials for use in certain applications, it comes down to which kinds of properties can you combine. There's always a trade-off, right? You have to trade off bending modulus or strength or tensile strength with corrosion and expense and price. And so what graphene is going to enable us to do is take the materials that we have now, conventional materials, and control whether they corrode, whether they are porous to certain gas molecules, porous to other molecules, and it's going to give us a new class of materials that will have the advantages of strength, but also have this corrosion resistance. It's a conductive coating, so you can also render conductive materials that are normally insulating, like polymers, your milk jug. If you want to start to put conducting elements or RFID tags and things into plastics, then carbon-based nanomaterials like graphene and carbon nanotubes are very useful for doing that. They're also they are very earth abundant. They're not mined from the earth in principle. It's not. You can make them essentially by burning trash if you need to. It's they're a process that can be produced from corn or ethanol. It's fundamentally different from, say, a mineral that has to be extracted from the ground, and for which the earth has a finite amount.